I'll begin with a word of prayer. So, Heavenly Father, we thank you for this morning. Thank you for the cool weather outside, and just pray that you be with us today. Help us to glorify you, what we do, and just help the students to understand, Lord. In your name I pray. Amen. I guess we should probably top hat, right? So, put that out here. Any questions while I'm messing around with this? So what we're covering today is graphing, more graphing, and so it's kind of graphing, and then in the middle we're going to do something called function operations, and then hopefully the last story arc of class in here we'll do study parabolas and such. All right, so that's the plan. So I'm going to start with an example from that's kind of in the same style, if you will, as last time. I won't quite follow the same exact format, but pretty close. 6103 is that. All right, so here's my, let's talk about, you talk about the thing we haven't talked yet enough about graphing is properties of graphs. All right, so I want to really talk about three properties today: even, odd, and what's called discontinuous. All right, but we'll lead off here with an example. So suppose you've got f of x equal to, 3 plus 1 over x minus 2 quantity squared. All right, let's graph this function. Okay, so the graph of this function, I'm going to start with what? I'm going to start with y equals to 1 over x squared, right? That's kind of the prototypical example here, right? That's the standard example this is based on. It's a volcano. It's going to be a volcano graph, right? And then I take that and I go right 2 units, right? And that would get me to y equals 1 over x minus 2 quantity squared, right? So I'm working on building the formula up there, right? One more move and then we'll be there, right? Now if I add 3 to that, so I want to go up 3, that gives us y equals to 3 plus 1 over x minus 2. So this would take three of those boxes in that template I gave you if we were going to do it that way. But so corresponding pictures are what we got. What we got? Let me get my markers out here. So the volcano graph is one of those graphs that has a vertical asymptote, right? So it's in our vested interest to pay mind to the vertical and also to the horizontal asymptotes as we're graphing. So I'm going to do that. Let me just get to it here. So we've got so to start with, we start with the volcano graph. It's got vertical asymptote of x equal to 0. It's got a horizontal asymptote of y equals to 0. And it looks like this, right? On our standard example sheet, it's in there, right? Then I shift right 2. So my vertical asymptote shifts over to here. The horizontal asymptote stays put. Then my middle graph looks something like this, right? And then finally I shift up by 3. So the vertical asymptote stays put at 2, yeah? And the horizontal asymptote moves up here to 3. And then finishing picture, it looks something kind of sort of like this, yeah? So there you go. That's the graph of y equals 3 over 3 plus 1 over x minus 2 squared, right? And this is a pretty straight down the middle kind of question. I hope you'd be able to do this kind of graphing on the test, for example. This is a little bit simpler than some of the examples I did last time, right? There's no reflection, It's just 3 steps, not 4 steps. So this would be a friendly. I would deem this a friendly test question if I said graph this. Yeah. Okay, so this is just our starting example. Now I want to introduce the next members in the story we're telling here. So the names of these characters are even function, odd function, and discontinuous function. So let me kind of give you a definition for each one of these characters. Even function, how we define that. An even function is defined to be one such that f of minus x is equal to f of x. So you could say this: an even function eats minuses. All right? Just gobbles them. Odd function, if you have f of minus x, you get minus f of x. So an odd function, if you feed it a minus, it spits it back out. All right? And both of these things have to be true for all x in the domain. All right, so they have to be true for all x in the domain. That's what we mean by an even or an odd function, respectively. Okay. And what's a discontinuous function? Well, okay, fine. To be honest, to properly discuss discontinuity, I do need the discussion from calculus. But for us, for the time being, we're just going to make do with the following. It has a jump in its graph. So we'll make do with that as our definition for discontinuous, right? Another way you could say that is if you're graphing it, you can't help but lift your pen as you're drawing the graph, all right? Now a function which is not discontinuous is also called a continuous function. Like many of our examples that we know and love are actually continuous functions. Okay, so I didn't like start early or something, did I? No. Like there's this one time I came to class, right? And I looked around and I was like, huh, there's not many people here, but I'm here. And I just started lecturing. And they didn't stop me. I just lectured for about 10 minutes, and all of a sudden, a bunch of other people came in, and I was like, oh, I realized that the class started like 10 minutes after when I started. And they just let me go. Like, they just let me, the students who were there didn't like stop me. It's like, come on, guys. If I start lecturing early, you gotta stop me. I don't think that happened today, though. Let's see here. So example 2. I have enough trouble getting here at 8:15, you know? Example 2. So let's look at y equals to, let's look at y equals to x squared, right? So think of that as my function. So this is an easy example. We know this one. We can graph this with a minimum of mental effort, right? It looks like this, right? That's the graph y equals x squared. Is this an even function? It is. Let's see why. So if we check it, f of minus x, right, is equal to minus x parentheses squared. What happens when we square the minus? It becomes positive, right? Poof, it's gone. So this is just equal to x squared, which, by the way, is equal to f of x. So this shows, indeed, f is even, right? This is an even function. Now, what I just wrote in red is the algebraic proof, if you like. It's the algebraic argument that this is an even function, right? What does it mean graphically? Like, how do we detect evenness in terms of the graph? What's it look like? How can we describe that? So if we look at this graph, it has, you know, this has the kind of shape that we want to say is an even function. And what's going on here, right, if you look at it, is that if you pick a point here, let's call it like a comma b, there's a partner point over here, right, of minus a comma b. And so there's always this pairing, right? Of every point to the right of the y-axis, there's a corresponding point to the left of the y-axis, symmetrically so, right? In other words, this graph is the same if you reflect it over the y-axis, right? If you reflect the graph, if you flip it over the y-axis, if you can imagine that in your mind's eye, we get the same graph again, right? So this has what's called symmetry. It's symmetric, rather, with respect to the y-axis. So that's another way we could describe an even function. An even function is one which is symmetric with respect to the y-axis. All right? You guys with me? Okay. So if I didn't give you a formula, right? If I just gave you a picture, here's the graph of a function, is it even? Right? If I just give you a graph and I had not given you a formula, you couldn't do what I did in red here, right? You don't have the formula. Imagine that. You just have a picture. You just have to rely on this principle. Is the graph symmetric with respect to the y-axis? That you could tell that. Whether, you could tell whether or not the graph is even or not. Go back to example 1 for a second here. Is this graph the final product here, right? This one. Is this even? See, this is not even, right? If you reflect this graph over the y-axis, you don't get the same thing back again, right? It moves the volcano to the other side, right? This is not even. I mean, more to the point, this is not symmetric with respect to the y-axis. Therefore, this function right here, 3 plus 1 over x minus 2 squared, it's not an even function. All right. Okay, so now, is this even? Yeah, it is, right? So we started with an even function. The volcano itself, the basic volcano, is even. But once you shift it around, it ruins the symmetry. So it's no longer even. At least it doesn't have to be. I mean, you could imagine doing enough transformations that you got back to symmetric or something, but not the case here. Example 3. Let's look at f of x equals to x cubed minus x. All right, so x cubed minus x. We're going to look at y equals x cubed minus x. Now what's that? Y equals x cubed minus x. So what we're going to do here, we will factor out the x. That gives us x squared minus 1. And then x squared minus 1, that factors, right? It's difference of squares. So we can factor that to x times x plus 1 times x minus 1. All right? From that formula right there, the factored form of the function, I can see that we have zeros at 0, minus 1, and 1. Those are the x-intercepts of the graph. So I draw my axes. What's wrong with me? Let's try this again. I'm violating my color coding. And also I need more room. Make it smaller. There we go. All right, so we've got a 0 at 0, at 1, and at minus 1. And the graph looks something like this. All right. There you go. That's y equals x cubed minus x. Now I've asked all my other sections the following question. Do you like time travel? No votes on time travel? Who likes time travel? If you enjoy time travel, that's what this is. This is next week, all right? So I haven't taught you guys this yet. We're going to focus on how to graph polynomials like next week, all right? So we're not there yet, but next week. So at the moment, I'm just doing this. Like, if you don't understand this yet, that's okay. We're going to see that if you can factor the polynomial, that tells you where the x-intercepts are. And then you need to kind of think about a sign chart, like we did with the inequalities. That'll tell you whether you're above the axis or below the axis, or maybe bouncing off the axis. Okay, that's a whole long story. That's not the point of this example. I just wanted to for us to have an interesting example to compare, to ask the question about odd here, right? Because this is in fact an odd function. Let's see why. Algebraically, Let's plug in f of minus x. What do we get? Minus x quantity cubed minus a minus x, right? So that's minus x cubed plus x. So in order to decide whether the function's even or odd, I have to try to see f of x in this formula. Can you see f of x? What if we factor out a minus here? Right? I can factor out the minus like that. And what's in the parentheses is the formula for f of x. It's x cubed minus x. So what we're looking at then is minus f of x. So therefore f is odd. Right? F is odd. This graph is not symmetric with respect to the y-axis, right? If you reflect the graph over the y-axis, you get a different graph, right? What is the symmetry here? What's the pairing? If I look at a point, a comma b, what's the partner point for that point for an odd graph? Sort of the mirror point in this case is down here, yeah? And that point would be like minus a comma minus b. So there's a pairing for an odd graph between points and they're negative. Right? For every point a comma b, there's a corresponding point minus a comma minus b on the graph. That's the symmetry of an odd graph. This is called, this kind of pairing is said to be symmetric with respect to the origin. So the origin is, 0, 0. That's what people say. They say this kind of graph is symmetric with respect to the origin. What they're thinking about is the fact that you can reflect the graph through the origin to the other side, right? If our graph had more stuff in quadrant 2, there would be a part of the graph that's paired with it in quadrant 4, right? Quadrant 1 reflects into quadrant 3 and so forth. But anyway, I don't know. This terminology, symmetric with respect to the origin, I've never found it entirely natural, but it's what people say. So, and you can see it. Any questions? So if I ask you, give me algebraic evidence that the function's even or odd, what I'm asking for is for you to work through and show me that f of minus x is equal to f of x, or to show me that f of minus x is equal to minus f of x, right? If it was even or odd. So these would be, what's in red, these are the algebraic arguments, right? On the other hand, of course, I could give you a graph and ask you, based on the shape of the graph, based on the geometry of the graph, is the function even or odd? That question you can ask without actually having a formula. Now, how about this back here? Is this graph even? We said no, right? Is it odd? It's also not odd, right? Because there's no pairing of this with something down here and this with something over there, like there should be if it was odd. There should be you should be able to reflect it through the origin. You don't see that. So this function is, in fact, in summary, neither even nor odd. So that might be a kind of question you face on the next test. Here's a graph. Is it even? Is it odd? Is it neither? All right? There's also some more basic thing here, right? Which is that in order to really ask the question of even or odd, you do need both x and minus x in the domain, right? You can't even really pose these questions unless you have a symmetry in the domain between the positive and the negative numbers, right? For every positive number, you have to have a corresponding negative number. If you don't have that, it's hard to ask those questions, right? So some things like the square root function, so remember the square root function on our graph? It's just half of the parabola turned sideways. Is that even or is it odd? The answer doesn't even, you can't even really ask the question because I would say it's neither even nor odd because you can't even find the minus x for x, right? Like the domain for the square root function is just positive numbers and 0. You can't try minus x for that function. Let me show you another example with even and odd. This one's a little bit more creative here. Example 4. So you're given half of a function, all right? Namely, y equals the square root of x for x greater than or equal to 0, okay? And then a, extend to even function, B, extend to odd function. All right. So I'm going to go about the answer here in kind of two different ways. Okay, I'm going to first do it graphically, and then I'm going to give you the formula. All right. And we're going to get a little bit more practice about transformation and graphs along the way. So here we go. So to start with, you're given, right, that you've got the square root function, right? So it's like, that looks like this, right? That's given to us. And I'm supposed to extend the graph. What's that mean? I need to pair this with something more to make it an even function. So what's missing? If I want my whole function to be even, what do I need to add to this? I need to reflect it, right, across the y-axis. So what I should add would be this guy. Right? Now that, in total, is an even function, the graph of an even function. What's its formula? So if I call this, you know, y equals, let's say, h of x, it's got two cases, yeah? It's got two cases. So case one, we've got square root of x for x greater than or equal to 0. But there's a case 2, right, for x less than 0. What's the formula for over here? What's the formula for the red part? Can you guys tell me?
Would it be like negative?
A popular negative square root. So you mean this?
Yeah.
But that, the graph of minus square root, remember, is a reflection over the x-axis. So that would actually be down here. Right?
The negative needs to go inside.
Do what?
The negative needs to go inside.
The negative goes inside. Yes, yes. So I like your answer. That's a good starting point. We just need to fix it a little bit, right? Put the minus inside. That's exactly what we need to do. So square root of minus x. Yeah, and there you go. That, in fact, is an even function. And we just, you know, you guys have heard of Build-A-Bear, right? This is build a function. So this example should cost like 3 times as much as a regular example, you know? But you made it, so that makes it worth 3 times the cost, right? Is it just 3 times? I mean, if you think about a stuffed animal in the wild versus a stuffed animal in Build-A-Bear, like what's the difference in cost? It's got to be pretty significant, right? So for example here, this point, 4 comma 2, right, because the square root of 4 is 2, gets paired with this point over here, minus 4 comma 2, right? Over here we've got the square root of minus a minus 4, which is equal to the square root of 4, which is equal to 2. That's why I get that point. That's how that formula works, right? We take the minus, that cancels, it gives you a plus, right? That's why we need the minus inside the square root, so that when we feed it the negative number, it still makes sense. Still gives us back a real number. And of course, on the flip side of things, this is totally unsurprising, right? Because to reflect this graph over the y-axis, we do what? We replace x with minus x. That's what you did. You took this formula and you replaced x with minus x. That's the reflection of the purple over to the red. All right, so part B. Again, I've got the square root to start with, right? And this time I want my extension to do what? I want it to do like this, right? So if you think about that, right? So let's say we've got y equals to, I'll call this one g of x. So the case 1 is square root of x for x greater than or equal to 0. That was given to us. The question is, what do we do for x less than 0? So we want, what's the formula for the red piece right here? Well, look at that, right? What is that? That's the reflection of the previous answer, part B, over the x-axis, right? Like what you want is you want to take this right? And you want to flip it over to that, don't you? So what's the formula now? Now we combine both of your answers. We get a minus the square root of minus x here. And that's what you want. Because that takes the previous one and flips it over. And there you go. That's an odd function, which extends the square root function. There's the even extension of the square root function, right? If you have a function which is defined just for positive or just for negative numbers, you can extend it in an even way, or you could extend it in an odd way. That's a meaningful homework problem. All right, next up, we should talk about discontinuous functions. And I'll give you an interesting example, which we haven't talked about yet, and it's kind of a weird example. It's called the ceiling function. So what's ceiling? Example 5. Ceiling function. And so here's my rough definition of it. The ceiling of x is equal to integer greater than or equal to x. It's equal to the integer greater than or equal to x. And what I mean by that, let's look at a number line just to keep things clear here. -2, -1, 0, 1, 2. There's my handy dandy number line. These are integers, right? Integers are whole numbers, and they're negatives, also 0. Okay? And so like the ceiling of, 0.2, and let's figure out what's the ceiling of 1.7, the ceiling of 2, the ceiling of -2.3. All right. If we can figure those out, then I think we pretty well understand the ceiling function. So let's talk about what those would be. What would the ceiling of 0.2 be? Is 0.2 an integer? It is not. So you go to the next integer to the right on the number line. So like 0.2 is here-ish, right? So the next integer up is 1. 1.7, it's like here, so you go 2. How about the ceiling of 2? It's the next integer greater than or equal to x. In this case, it is an integer, so the answer is just 2. Okay? So this is like a really kind of ridiculous way of rounding, right? If you round this way in your other classes, you'll be wrong about half of the time, right? Because we usually only round up for like 5 or larger in the next place, right? That's the standard. How about -2.3? What's the ceiling of -2.3? What is it? Is it -3 or is it -2? -2. It has to be a number, an integer greater than or equal to that. So -2 is greater than or equal to -2.3. So this is the ceiling function. What's its graph look like? The graph of the ceiling function. So we've got ourselves 0 maps to 0, right? But then 0.1 all the way over to 1 maps to 1. And then let's see here. So let me draw a few more and talk about it. So this would be like -1, -2, -3, 1, 2, 3, and so forth and so on. It's what it is like an infinite staircase, the graph here, So, I mean, it's pretty weird, right? I mean, we have seen nothing like this graphically up to this point, have we? I don't think so. This is nothing like x squared, x cubed, the square root, the cube root, the volcano, the reciprocal, all these other functions. really not like this at all, because this really belongs to a different course. I would say that this belongs to a course in what's called number theory, or perhaps discrete math. So I would say it's a foreign example in a very real way. But this example has tons of discontinuities, right? There's a jump in the graph at every integer. See that? So discontinuity here, discontinuity there, discontinuity, discontinuity. Tons and tons of discontinuities in this graph. This graph is rather discontinuous, all right? All right, before we're done with this graph, let's ask a couple of easy questions here. What's the domain? So I'm saying f of x, y equals f of x equals to the ceiling of x, right? So I'm thinking of the ceiling as my function. What's the domain of f then? What's the range? We all need more practice on domain and range for sure. The domain here is kind of easy. It's everything, right? Because we've defined the ceiling for any number, it's just the next integer, so the domain is just everything. All x values are covered. How about the range though? The range is kind of weird, right? It's just whole numbers and their negatives, right? It's things like what? Like ... -3, -2, -1, 0, 1, 2, and so forth, right? Sometimes I write that set more compactly as 0, ±1, ±2, ... right? That's just an easier way to write that set. Do you guys know what this set is called? I don't think I've talked about it before in here, but this is exactly the set of integers, right? So the range here is integers. The notation for the set of integers, if you guys are wondering, is like this funny looking z. So this is the set of integers. You might say, why z? It goes back to when Germany was like more important to mathematics. It used to be the center of mathematical progress for the world back before that thing called World War II, when we got all their good scientists after that. Ha ha ha. But yeah, so the German word for numbers is Zahlen, and so that's why it's z. We good? Okay. So that's pretty much it. That's all I have to say about properties of functions. So let's move on here to the next story arc. Today is operations of functions, and also how to build new functions from old. All right, so we can take two functions that are given, and we can put those together to make a new function. All right, and so let's do that. So, operations on functions. AKA, also known as new functions from old. So here's the context. You're given functions f and g, right? We construct, create, build, whatever you want to say, define, right? New functions. F plus g, f minus g, a constant times a function, a product of two functions, f times g, a quotient of two functions, f over g, and finally the composite of two functions, f composed with g. These are all new functions we can build from a pair of given functions. Let me write down the words I just said. So this is the sum, difference, scalar multiple. Here, that c is just a number, okay? So another fancy word for number is scalar. So a scalar multiple. And here we're looking at the product of two functions. Here we're looking at the quotient, right? And then last but not least, f composed with g. This is the composite of f with g, where g is the inside function, all right? And by the way, f is the quote-unquote outside function. So when you're understanding the composition of two functions, it is critical to understand which is the outside function and which is the inside function. All right, that's so much of the pattern recognition involved in composition. It's just that. So at the moment, I've just called names, right? So how do we actually define these things? Oh man. This spray bottle's not well. Oh well. So I'll put the definitions over here. So we have like f plus g of x is f of x plus g of x. F minus g of x is, guess what? F of x minus g of x. Okay? A constant times f. That function, when you feed it x, you get out c times f of x. All right. F times g of x is equal to f of x times g of x. F divided by g, acting on x, is defined to be f of x over g of x. All right. So far, all of these are kind of like, I don't know. Like, of course, what else would you do, right? If I didn't write any of this on the board, you probably would already assume these formulas, right? I don't think there's anything like deeply surprising here, right? What if I said g over f of x? What would you tell me? What's that defined to be? We do what? What divided by what? G of x divided by f of x, right? I mean, so these two, they come with strings attached, right? In order for these to make sense, what do we need? We need g of x to be non-zero, right? And over here, we need f of x to be non-zero. That's true, all right? But now the composite. The composite is something different. So f composed with g of x is by definition f of g of x. In contrast, g composed with f of x is g of f of x. And see, that's, I'm not just multiplying the functions. I'm actually feeding the formula from the one function into the formula for the other function. There's something more operationally nuanced there than all of these rules. These rules are just arithmetic on the given formulas, right? Those two formulas require thinking. Now, I would point out something here before I go on. Notice that f of x times g of x, this is just the product of two numbers, right? You can multiply, is 3 times 5, 5 times 3? Of course it is, right? In the same sense, this is g of x times f of x, right? And so g of x times f of x is gf. It's the function gf of x, by definition. So what I'm telling you is the function f times g is the same as the function g times f. The product of functions commutes. F times g is g times f. What about the quotient? Does the quotient commute? Is f over g equal to g over f? I mean, they're related, but they're not equal, right? They're reciprocal to each other. So there's a difference between the quotient one way and the quotient the other way. It's better to think of a composite as being more like a quotient and less like a product. I know the notation, in some sense, resembles the product, right? But it is very different because the composition in one way does not have to be equal to the composition in another way. Function composition does not commute. Function product does commute. They look similar, but they're quite different. So that's one of the fundamental confusions of this part of the course, so I'm mentioning it. Maybe this is a self-fulfilling prophecy. Now that I've told you to confuse them, you're going to do it because you're good students, right? And you just follow what I say. No, don't do that. Don't let this be a self-fulfilling prophecy. Do not confuse f composed with g with f times g. As some people like to say, don't get lost in the fog. But I wouldn't say that. What am I? Example, I've lost track of my example number. What is it? 5, 6, 6? Okay. So example 6. Let's take these definition out for a spin. F of x equals, let's say, I don't know, for you guys, the cube root of 2x plus 3. All right, and g of x equals to 1 over x squared plus 1 there. Okay? There you go. There's two functions. Let's add them, subtract them, multiply them, divide them, and compose them. So here we go. Let's illustrate. F plus g of x. We'll do f minus g of x. We'll do f times g of x. We'll do f over g of x. And then finally, we'll do f composed with g of x. All right, so what's the formula for f plus g? All you do is you add the formulas. Very silly, right? Hooray. Okay. F minus g, subtract the formulas. All right? Now, got to be careful with the subtraction. If your formula looks a little different, be careful to apply the minus to everything in the formula. All right? In the example I picked for the other sections, we had like a sum for g, and when we subtract, we have to be careful to subtract both things. Okay? So watch out for that. In other words, think about putting a parenthesis around the formula for g as you're doing the subtraction. Now, f times g, that's just the cube root of 2x plus 3 times 1 over x squared plus 1, right? And so we could rewrite that as follows. We could rewrite that as the cube root of 2x plus 3 all divided by x squared plus 1. That's a good way to write the answer here. Yeah. There's nothing deeply significant about what I just did there, though. I'm just using a different notation for the same algebraic expression. It's not really that profound or anything. F over g, literally the cube root of 2x plus 3 divided by g, which is 1 over x squared plus 1, yeah? I guess since I went down this path, can you guys simplify the formula here for me? How would you simplify that formula? You want to write it as a simple, not write it as a fraction. You can do what? What happens if you're dividing by 1 over x squared? What is this? That's the same as multiplying by x squared plus 1, right? So this simplifies to just x squared plus 1 times this cube root of 2x plus 3. All right. All right, so now we've reached the composite. Let's see if we can do this one. So what we want to do is f of g of x, right? What is g of x here? It's f of 1 over x squared plus 1. So what does that mean? That means that you take the formula for f, right? Which is the cube root of 2 times the input. What's the input here? 1 over x squared plus 1. And then I add 3. So there's the composite of f with g. On the other hand, if we do g composed with f, how's that go? That would be g of f of x. What was f of x? F of x was the cube root of 2x plus 3. All right? How's that go? Well, we have to plug in cube root of 2x plus 3 into the formula for g. What's the formula for g? It's 1 over the input squared plus 1. 1 over the input squared, which in this case is the cube root of 2x plus 3. You square that thing, you add 1. I think we can agree, right? These are not equal. Do you see that? Is f composed with g equal to g composed with f here? You've got a cube root of this monstrosity versus 1 over, I guess, the 2/3 power of 2x plus 3 plus 1. I mean, these are not the same, for sure. So the order of composition matters quite a bit, right? How many of you are not comfortable with the composition I just did? It's okay not to be comfortable. Some, right? So I have a strategy here, a way we can include extra steps to do the composition. If you're not comfortable with what I just did, I have a strategy for you. Let's try the strategy out. Let me show you how it works. So here's some, if you like, kind of training wheels to put on that calculation. And I would say maybe these are good wheels to never take off. So like f composed with g of x. How can we do that? F composed with g of x, I can think of as, well, it is f of g of x, right? So I can just think of it as f of g, where g equals to, well, in this case, 1 over x squared plus 1, right? What would f of g be? F of g would just be, put g in the place of x. So my f is cube root of 2g plus 3. Right? You guys get that, right? That's not a mysterious step, is it? All I'm doing is changing the letter x to the letter g. We get that? Now, once you get that, substitute the formula for g into that. And I forgot to add my 3, right? And there you go. That's the formula for f composed with g of x. We just make it into 2 steps. Step 1, write the formula in terms of the inside function as a letter. And then step 2, substitute the formula for the letter into the expression that you have. And that way you can kind of divide and conquer the problem. Let's do g composed with f for this way. So I think, well, that's really just g plugging in f, right? Where f is equal to what? F is equal to the cube root of 2x plus 3, yeah? So going through that, what's g of f? The formula should be 1 over f squared plus 1, yeah? And now I just plug in what f is, which is 1 over the cube root of 2x plus 3, square that thing, add 1. As you can see, I got the same exact formulas, right? Here and here as I did over there. The difference is I didn't just do it in my head, right? I wrote down a step that maybe you can follow. If you want, you could call this the method of substitution. All right, the method of substitution. Another way to look at it is like, you could just like, whenever you have a formula, you could rewrite the formula in terms of another letter, you know? Like if I have f of x equal the cube root of 2x plus 3, I can do f of, say, u is the cube root of 2u plus 3. You know, and then I can think about setting u equal to the inside function is a way you could think through it as well. You know, it's a substitution is what it is. Any questions? So I hope that helps you sort through some of the composition questions. There's another kind of way these problems come to us, which is numerically. What if you don't have a formula for f and g? What if you just have numbers? Right? What if you just have numbers? How does that go? So like example 7, you might be given f of 2 equals 6, f of 3, excuse me, g of 3 equals 7, and f of 7 equals minus 11, right? Suppose you're given this data, right? Then you can ask questions like, what's f plus g of 2, you know? What's f minus g of 2, yeah? What's f times g of 2? What's 17 times f of 2, right? These are all things we could try to ask and answer. We could also look at f composed with g of 2, and we could even try g composed with f of 2. Now, at least one of these questions won't be answerable with the given information. Let's sort through it. Let's see which one breaks down. What's f plus g of 2? It's what? By definition, f of 2 plus g of 2, right? Which is what? 6 plus 7, right? So the answer to the first thing here is 13. How about f minus g of 2? It's what? It's just 6 minus 7, right? What about f times g of 2? There we do f of 2 times g of 2, right? Which is, in this case, 6 times 7. What about 17f of 2? There we just multiply 17 times f of 2, whatever that is. Apparently 17 times 6, which is 60 plus 42, which is, I guess, 102. Now finally, so up to now, I argue that I really didn't have to think that hard for these. Yep.
Sorry, where did you get the G of 2 equals 7?
That was given. Oh, did I not? Oh my goodness. Thank you. Oh, sadness. All right. G of 2 is 7. What is it about this time slot? Like, I have covered the material that we're up to right now in 50 minutes in every other section. But in this section, somehow it takes me, I'm already at like 54 minutes. I don't know what's going on in here. It's just this time slot, like 8:15. I do not think properly at 8:15, personally. Anyway, so actually, I blame it's all you. It's all your fault, all of you, because you guys aren't asking me questions. Asking me questions helps me stop blathering sometimes. So left to my own devices, I'll just ask my own questions, which always take longer to answer. F of g of 2 and g of f of 2 is what we'd like to calculate. F of g of 2, well, that's f of 7, right? What is f of 7? Well, that was given to be minus 11, right? So we're good. But f of g of f of 2 is g of what? G of 6, right? So to answer that question, we don't have enough information right now. As it stands, you'd have to be like, no, you can't ask me that. You haven't told me enough. There's different ways we could add that information, right? Let me show you in kind of a different way. What if we had a graph of g? What if we had a graph of g? What if the graph of g was given, and it looked like, well, g of 2 goes through 7, right? But g of 6, who knows where it does? 2. So maybe the graph of g looks like this. Right, so there's 6. Okay. So maybe you're given, suppose you're given this graph. Okay, imagine that. So add that to the things which are given. Now we can answer the question, what's g of f of 2? It's g of 6, right? What is g of 6 here? I don't know if you can see it or not, but I tried to draw it so that the graph of g goes through the x-axis at 6, right? So that means that g of 6 is equal to what? 0, right? So if you're given that graph, then the answer here would be 0. So all I'm trying to get across to you guys is, as they ask you questions about function operations, there's really kind of 3 ways they can go. They can give you formulas, right? They can just give you like sets of values like this, just tell you ad hoc, these are the values, figure stuff out, right? The other way they can do it, which I think you guys tend to find more challenging, is they give you a graph of the function, and then they ask you questions about new functions based on maybe a graph of f and a graph of g that you're given, right? Or you could be given another problem where you have the formula for one function and the graph for the other, figure out things about the sum, the difference, the quotient, and so forth, right? These are all different flavor options. Anyway, that's all I got to say about that. So I'm going to move on. So we need to talk about parabolas. Now, to be fair, I'm not really talking about general parabolas. In particular, I want to discuss what is the graph of y equals ax squared plus bx plus c, right? Where a, b, and c are real numbers. And we also know that a is not equal to 0. Right? So what is it? What can you say about the graph here? In other words, how do we graph a parabola? What do you need to know? What are the really salient features of a parabola? What makes it a, what defines it uniquely? And so I would say that let me just show you the answer, and then we'll kind of work through the algebra. But basically, somewhere there's a vertex, right? There's a vertex for the parabola. Let's call that h comma k, right? The vertex is at h comma k. And then the parabola, maybe it opens up like that, right? It could open up like that. In that case, there's also something like, what's another case though? It could be that your parabola is like over here, right? The vertex is below the x-axis, yeah? And it opens up. Like that, That might be the case. If it opens up like that, then we can also look at roots, right? Say R1 and R2. We can look at where it crosses the x-axis, right? It has x-intercepts. Now, both of these pictures, they assume what? A is greater than 0, right? So it's opening up. So it either opens up from a vertex that's above the x-axis or a vertex that's below the x-axis. Or what's the third possibility? It could also be what? It could also look like this, right? It could be that the vertex is on the x-axis, right? And it just, goes like this. Now my pictures are starting to overlap. Sorry about that. Let me try to stop short here. Okay. Sorry, my picture's getting kind of busy. But there's 3 other cases to picture as well, right? There's 3 corresponding pictures to think about when A is negative, right? Because it could open down with the vertex above the x-axis. It could open down with the vertex on the x-axis. It could open down with the vertex below the x-axis, right? At the risk of making this too muddy, here I'll do this one on the x-axis